I'm Max. I work at Autodesk on AutoCAD Mobile. I lead a team of three C++ engineers. So what we do is work on the engine, specifically from the mobile side. Currently, we're undertaking a massive project, which is taking a 35 years old, well-aged code. I mean, code that's been worked on and making it work on multiple platforms. So in this talk, I'm going to present some of the decisions we made in terms of communicating between threads and how it benefited us after quite some time after doing that. So, agenda. So I'm going to intro you to AutoCAD. Those of you who don't know, then following that, we'll talk on the bulk of this presentation, which is cross-thread communications. And generating cross-platform APIs, this connects strictly to the second point. And dividends, how did it benefit us? So intro to AutoCAD. So what's AutoCAD anyway? Those of you who don't know, it's the flagship of Autodesk. It's a CAD app that means it allows you to sketch drawings both in 2D and 3D. It's basically like the assembler of CAD. You can do anything. You can do architecture, construction, electrical, mechanical, whatever you want. It's super extensible. Like I said, code is 35 years old, nearly 36 now, worked on since 82. And we actually target C++14, which is quite astonishing. We're like trying to always work bleeding edge. When 17 comes out, we're gonna be there. So it's pretty cool. So some feeling of how it looks like. So here it is running on multiple platforms, and on the top left, you can even see it running on DOS. So it's quite an old version, but still DOS. It's quite awesome. And on the right here, so on the left is UWP. On the right, you can see it running on the web. We're actually using WebAssembly. We compile the whole bunch of code and it runs on the client side. And this is quite amazing. You can access AutoCAD web.autocad.com and check it out yourself. So let's talk about the elephant in the room. It's cross-thread communications. So AutoCAD is kind of like I just mentioned, originates in DOS. So when being in the DOS days, you used to poll for input events, kind of ugly. Then following that, so most of its life was spent on Windows. So in Windows, you probably are familiar with the message loop, which is this pile of code. So the message loop is nice and dandy if you're on Windows. Everything works on the same thread. And it's worth mentioning that AutoCAD is a single-threaded application. Everything, even the graphics, everything on the same thread since ever. And, well, that's nice. But, well, on web and mobile, nope. You can't do that because this will happen to you. On Android specifically. Anyway, meaning it will crash if you do long operation on the main thread. It will stall, it will do something unexpected, you just can't do it. So what we chose is dual threading. So we divided the app into two parts in terms of threads. So there's the UI thread, which we get for granted from the operating system. And from the web, we just get whatever the browser gives us. And there's the app thread, which we create ourselves. So on non-web platforms, that's a std thread, and on the web, it's a web worker. And what I want to talk about is something we call the messaging API. Is the protocol we use to communicate between those threads. And so here's the high-level architecture. Just gonna go about this briefly. So UI thread contains the anything the OS gives us in terms of UI. That's client-side code, language specific. Let's say if you're on iOS, that will be Swift. If you're on the web, it will be TypeScript. Then we have the generated APIs, which are contain the messaging API, which I'm going to talk about shortly. And this is actually the cross thread bridge, that on the UI thread you get a language that is specific to the platform, again, like Objective-C for iOS or TypeScript for the web. Then the most bulk of our application is the common C++ code shared among all platforms. And then we have a small layer of platform abstraction, which is essentially function calls like find all fonts, enumerate fonts, or get me some directories, stuff like that. So let's talk about the messaging API protocol. So consider that a user wants to open a drawing in AutoCAD. So what happens is a message flows from the UI thread to the app thread saying, okay, what's the action? Open document. What's the payload? Let's say it's a drawing called Colombia, and there are two addresses, one for failure and one for success. So essentially, those addresses mean where to go back once a response comes back from the app thread to the UI thread. And in this example, the first one is a success. So the address comes back is the same address that we sent, and with the payload of the file name, let's say. And the second example is of an error. So we use an API we call an action API called postString, which is essentially do something on the drawing. Let's say we draw a line, but we have a typo. So what we get from the app thread is a payload with an error message, an error code, and an address that points to the error. So let's discuss a bit architecture. So now we see the protocol, now architecture. So UI and app. Let's talk about the boxes inside the boxes. And the first one being the proxy. So on the UI thread, I mentioned that we have APIs that are specific to the platform. We call that the proxy. It is generated code. And on the app thread, we have C++ abstract classes, which are also generated. And the abstract comes in form of pure virtual functions, which you need to implement manually. And below it, you can see the stub impl, which inherits the generated stub. So yeah, and the stub impl is a concrete C++ class. In both threads, we have something we call a channel, and those channels communicate with each other via a message queue. Another part worth mentioning is the code generation pipeline, which I'll elaborate later on in this slide, which consists of a code generator that generates those proxy and stub parts I mentioned. And we have an IDL that defines the API, and some templates, not C++ templates, just source templates, which define both the proxy and the stub, how they should look like in each language. So code, deep dive. Let's see some code finally. So what I'm going to do is start from the topmost level. You can see that's level 0. We're seeing Swift code, rather simple. So we create here the proxy object I mentioned. So in this case, it's the AutoCAD app proxy. We shoot open document with a file name. There are two callbacks, success and failure. The implementation is trivial, just printing something. And let's dive down another level. So that's Objective-C. That's generated code. Here we can see that what we firstly do is create something we call a continuation. So if you recall, in the protocol, we've seen addresses of success and error. So this continuation gets registered into a dictionary that it encompasses the address. And what this continuation holds is the success and error callbacks that have been passed down from the level 0 we just seen, and can be accessed at a later time. So once we create the continuation, we get the address. Now we create the message itself, which is open document. And then we get to the channel, and we say, okay, post message. Here we are posting the message. So here you can see the message queue. There's nothing really to it. Here it uses a std logguard and std mutex to protect it. And we have a conditional variable, which we'll come back to it in a further slide. And finally, the message loop, which you can see is in the up thread. In a nutshell, what it does, it checks whether something new in the message and does a dispatch if there is. So now we'll deep dive a bit into how the message queuing works, but before I do it, I want to talk about the problem we've encountered. And this problem is the queue congestion. So basically, when you see a queue like that, and you know that a new iPad is out or an iPhone, that's what happened to us. Essentially, in touch devices, you have a gesture called pan, right? When you just drag your finger around the screen and you want to walk around the drawing. So the queue got blown up with thousands of messages, and for each message there was some CPU we had to pay, CPU time we had to pay, because code was executed. So the solution we chose for that is message coalescing, meaning essentially we go throughout the queue. Okay, we use here the algorithm stood remove if, and we apply a filter, which is a predicate, and anything that matches this predicate just gets removed from the queue. So in the case of pan, it only keeps the latest, most recent message, because we don't care if in the split second that the user moved his finger, there are any other messages that show a really small diff, because it's not noticeable. And it solved our problem. It also applies for different kinds of other messages, such as timer messages and whatever that is duplicated and can be thrown out. Let's go forward. So, going back to pop, which we've seen in the message loop. So you remember the condition variable. So here it is. Essentially, what pop does is most of the time it sleeps. So the user interacts with the UI up until the user interacts with the up thread. Then only then it will wake up, because then a message is available in the queue. So this condition continues. We go to the coalesce, to the coalesce function which we just saw, and make the queue nicer. And then finally, dispatch message. Dispatch message does the actual bulk of logic on the up thread. What it does, it looks up a stub implementation in a map according to the action specified in the message. So let's say we have the open document, so there will be action, so there will be a stub for that. And here we execute invoke on the stub, and then finally we post the result back to the proxy, which is the up thread. So let's dive a little bit more. So the generated code of the stub looks kind of like that. It's just a simple router. It basically looks for a string, open document, and executes an open document function which is implemented by the user. So this is generated code, and this is handwritten code. This is the stub implementation, quite simple. So it just calls open doc within the code, returns the result, and everyone's happy. So going forward, once we get some kind of a result from the stub, we want to route it back to the proxy channel. And the way we do it, we use the PAL, and in it we have a run on UI thread, which per platform is implemented to delegate a certain lambda call onto the UI thread. So, and here inside it also calls dispatch message in the channel. And what it does, if you recall, and if you did not forget the continuation object I showed initially, so we come back to it, the continuations map. We look back onto the address and choose either a success or failure. I actually have a bug here, it's fail and goes to success, but let's assume it's not here. Anyway, so that's the creative part, the code part. Let's go on with how we generate those APIs, those stub and proxy objects. So basically what we do is we employ an IDL. We chose C# as that IDL. Why we chose C#? Well, to be frank, we just had some code that already does that in another place. But another good reason is that reflection is just so easy with it. And this is what we employ to go throughout the IDL and understand which APIs we have to generate. It's very rich, it's very easy to handle. And for the template engine, we use the T4 template engine, which is built into Visual Studio. It also just comes with Visual Studio, so it's easy. Okay, so example for the IDL. So the font kind of messed up. Okay, never mind. Open document, familiar. C#. Next. T4 template, a bit ugly, but what can you do? So C# code uses reflection, so M type is a reflect type from that IDL we just seen. And this is just plain text. Specifically, this is Objective-C, showing the protocol. And here you can see a for each loop. You can just mix and match. It's super ugly, but just works. You know what's uglier? Do it all by hand. So yeah, so imagine like 6 platforms. No. Okay, so the generation pipeline works like that. We take the IDL sources, we compile them into a DLL, say message API definitions.dll. Then that DLL gets read by a code generator, which has the T4 templates embedded. And finally, it emits code for any target language we wish to use. So for instance, Kotlin, TypeScript, Objective-C, C++. And this code is the proxy and stub code. Then finally, why do it? Why do it like that? So for us, specifically for our case, like I said, single-threaded, it's just easy to do it this way. And another reason is what we can reap from it. So since this is a client-server architecture, we can change the threads into processes, right? Super easy. Because you have a JSON, it kind of reminds us REST APIs. It's very similar. So what we did is, in the client side, we wrote end-to-end tests that run on all platforms simultaneously. How we did it? We took Facebook's Jest unit testing framework, and we hooked it up to the messaging API generated in TypeScript, and we deployed the app to any platform on any device, run tests, get results, and here you can see an iPad, and here you can see the web, and you can see the UWP app, and finally Android. Just works, and it's quite astonishing because we get test results from all platforms at the same time. If it breaks in one platform, it discovers some new area of code that not necessarily is in another platform, and it's just awesome. Questions?
I didn't get it. What were you testing?
Yeah, so
platform, which part?
Yeah, so that's end-to-end testing. It's like an integration test. Okay, cool. Sure. שאני מעביר קוד ל-UI thread? כן. אני עושה dispatch, כאילו אני עושה run on UI thread דרך קריאת פל, אוקיי? שנגיד באנדרואיד זה פשוט לעשות פוסט להנדלר, אוקיי? למשל בג'אווה, דרך JNI, בסוויפט דרך ה-GCD. כן, כן, כן. אז כך שכל הקולבקים בסוף הם נקראים על ה-UI thread וזה מאוד צפוי למשתמש. הוא מבחינתו, הוא ב-UI thread וגם מקבל תשובות ב-UI thread. Questions anymore? כן. אוקיי, אז So this is T4. Well, basically, let's look maybe on the IDL. So basically, we have an open document declaration. We compile it into a DLL. Okay. Going forward, another app called Code Generator reads this DLL and employs reflection by getting all functions from that class and using them to generate like textual code. It generates basically text files, right? So let's say mtype name is name of the type. In the previous slide, the name of the type was let's say app. Okay. So that would say app. Let's say this constant says AutoCAD, so AutoCAD app. And does it make sense? More, yeah, okay.
So you wrote the template in T4 language.
Yeah.
To get your own whatever you need.
Yeah, whatever I need. So
for every platform.
Yeah, so I have Objective-C, I have Kotlin, I have TypeScript, the same language, T4, and
Did you use Kotlin for
Android.
And do the types map from C# to any platform?
To the types, yeah. I mean, for each platform, we inject the type information. Well basically, if you let's say it's actually not a great example. Anyway, the types are converted to the platform specific types. So let's say you have a string in C#, it will be converted to NS string star in Objective-C. Okay, or to std string in C++, and etc.
you consider open sourcing this?
Possibly, yeah.
It's in discussion.
Yeah, I have it in my mind. Yeah, I need to get the approvals, but yeah, I don't see any reason why not. It's not a big trade secret.
Mind telling a couple of words about your build process for all those different architectures? How do you manage all of that? It's usually a challenge.
Yeah, it is a challenge. I mean, we have a custom CI for that, so it runs all platforms simultaneously. Builds for all of them, including running tests. We have pre-flight commits, meaning that when you go to a branch in Git, so prior to submission, when you open a pull request, it builds on all platforms, so you know your health. I mean, it's not quick. I mean, today I built and it took like 7 hours to know. We need to still to scale. We have work to do there, but we're getting on the right path.
Pre-commit tests?
Yes. Exactly. Anything else? Okay, then gonna go a bit further. Okay, so we're hiring. Yeah, so if you wanna ask about it, just come to me. And finally, thank you.